In this video, we're going to start looking at how the sums of series may be calculated. We're going to meet three different methods of calculating or simplifying series. We may be able to get somewhere by using the method of proof by induction, and we may be able to use standard results and the properties of sigma notation that we have already established. And we'll be using these two techniques in this video, and then in the next video we will be using something known as telescoping series, or which is also known as the difference method for simplifying series. We need to make sure that we're aware of the standard results about pairs of integers, and you will probably have already seen and produced your own proofs of each of these results using the method of proof by induction or some other method. Now we're going to have a look at this by considering the example where Sn is the sum between r equals 1 and n of r times r plus 3. And we wish to prove that Sn is equal to 1/3 n plus 1 n plus 5. And once we've done that, we're going to deduce the value of the sum between r equals 51 and 100 of r times r plus 3. Now, the proof part of the question can be done either using induction or using the standard results and properties of sigma notation. So we'll start off by trying to produce a proof of the result by induction. Now, if we're going to do it by induction, it's well worth actually moving away from the sigma notation and thinking of the result in its expanded form. So the sum we're considering is the sum of 1 times 4, that's the value of r times r plus 3 when r equals 1, plus 2 times 5, that's the value when r equals 2, plus 3 times 6, all the way along to n times n plus 3. So all we've done is we've written Sn out in its expanded form. So what we really want to prove at this stage is that Sn, or in other words, 1 times 4 plus 2 times 5 plus 3 times 6 plus n all the way along to n times n plus 3 is equal to 1/3 n plus 1 n plus 5. And we're going to start by producing this proof using the method of induction. So, if we're going to prove this result is true by induction, we must start with the case when n equals 1. When n equals 1, the left-hand side is simply 1 times 4, which gives me 4. Whereas the right-hand side is going to be 1/3 of 1 times by 1 plus 1 times by 1 plus 5. In other words, it's 1/3 times by 1 times by 2 times by 6. So that's 1/3 of 12, which is 4. So we've got the result is correct, it's true for n equals 1. And then the second step in our induction is that we must assume the result is true for n equals k and deduce that the result is also true for n equals k plus 1. So, considering the result when n equals k plus 1, we've got sk plus 1 is 1 times 4 plus 2 times 5 all the way along to k times k plus 3, and then a final term of k plus 1 times k plus 4. And we've got to try and show that that is equal to 1/3 times by n plus 1 n plus 5, where n is k plus 1. So our target expression is 1/3 k plus 1 times by k plus 1 plus 1, times by k plus 1 plus 5. Now that target expression, of course, can be simplified a little bit to just 1/3 times by k plus 1, k plus 2, k plus 6. So we've now got to try and fill the gap between what we know sk plus 1 is and what our target for it is. Now looking at where we are at the moment, we know that sk plus 1 is 1 plus 4 plus 2 times 5 all the way along to k times k plus 3, and that of course is just sk, and then we've got k plus 1, k plus 4 added on. So we can say that sk plus 1 is sk plus k plus 1 times k plus 4. Now, we're assuming the result is true for n equals k. So sk is 1/3 k times by k plus 1 times by k plus 5. So we've got sk plus 1 equals 1/3 k, k plus 1, k plus 5, that's the sk, plus the final term, k plus 1 times k plus 4. Now looking where we are aiming for our target expression, we'd quite like to have a common factor of 1/3, we'd quite like to have a common factor of k plus 1, and we've already got those in our expression for sk plus 1. We've got 1/3 and we've got a k plus 1 as a factor that we can pull out. So we're going to extract that factor of 1/3 k plus 1 from this expression. So that's 1/3 k plus 1. Now the first term in the line above was 1/3 k, k plus 1, k plus 5. We've already picked up the 1/3, we've already picked up the k plus 1, so we're left with the k times k plus 5 for the first term. For the second term in the line above, we've got k plus 1 times k plus 4. We've pulled out 1/3 k plus 1 as a common factor. So to get k plus 1 times k plus 4, we're going to need inside the brackets 3 lots of k plus 4. Now, k times k plus 5 plus 3 lots of k plus 4 expands out to give me k squared plus 5k plus 3k plus 12. In other words, it expands out to give me k squared plus 8k plus 12. Now if we look carefully, k squared plus 8k plus 12 factorises to give me k plus 2 times k plus 6. So we've now arrived at our target expression. So we've got sk plus 1 is precisely what we want it to be, which is 1/3 of k plus 1 times by k plus 1 plus 1 times by k plus 1 plus 5. So we know that if the result is true for n equals k, then it is also true for n equals k plus 1. We know the result is true for n equals 1 by the first part of the induction. If it's true for n equals 1, then it's definitely also true for n equals 2 by the second step. If it's true for n equals 2, then it's also true for n equals 3 by the second step again. If it's true for n equals 3, then it's true for n equals 4 by the second step again. And we can keep going along and deduce that the result is therefore true for all positive integers. So we've produced our proof of the desired result by induction. Now the second way we can do the proof is by using the standard results together with the properties of sigma notation. So we've got Sn is a sum between r equals 1 and n of r times r plus 3. R times r plus 3 is the same thing as r squared plus 3r. So we've got the sum between r equals 1 and n of r squared plus 3r. Using the properties of sigma notation, which we've got, we can split that up as, first of all, the sum between r equals 1 and n of r squared, plus the sum between r equals 1 and n of 3 times r. And then, using the second property of the sigma notation, we can adapt that to being the sum between r equals 1 and n of r squared, plus 3 times the sum between r equals 1 and n of r. Now, we've also, at this stage, got the results about sums of powers of integers. We know that the sum between r equals 1 and n of r is just the same thing as a half n plus 1. And the sum between r equals 1 and n of r squared is 1/6 n plus 1, 2n plus 1. So the sum between r equals 1 and n of r squared is 1/6 n plus 1, 2n plus 1. And then we've got plus 3 times the sum between r equals 1 and n of r, which is a half n plus 1. Now if we look at this carefully, we have got a sixth we can take out as a common factor. We've got n is a common factor, and we've got n plus 1 as a common factor. So at this stage we'll extract a common factor of 1/6 n times by n plus 1. So there's my common factor. For the first term, I've already picked up the sixth. I've picked up the n, I've picked up the n plus 1, I haven't yet picked up the 2n plus 1. So the first term, all I need to put inside the final bracket is 2n plus 1. If we look at the second term, we've got 3/2 n plus 1. So I've certainly already picked up the n, I've picked up the n plus 1. To get the 3/2, I'm going to need to multiply 1/6 by 9. So to pick up the 3/2 n plus 1 term in the second bracket, I just need add 9. That second bracket clearly simplifies to 2n plus 10. I've now got a factor of 2 in that second bracket, so if I pull that factor of 2 out and combine it with the sixth, so I've got 2/6 or 1/3 times by n plus 1, n plus 5 as required. So using the properties of sigma notation, I've got quite a neat proof of the desired result. For the final part of the question, we had to deduce the value of the sum between r equals 51 and 100 of r times r plus 3. And that is going to be the sum of all of the terms from r equals 1 to 100 of r times r plus 3. Then I need to get rid of the terms that I don't want, which is all the terms between 1 and 50 of r times r plus 3. So what we've got is S100 take away S50. In other words, we've got 1/3 times 100 times 101 times 105. Take away 1/3 times by 50 times by 51 times by 55, which gives me a final total of 306,750. And now, if you've got a little bit of time still to spare, why not have a go at one or even both of these two questions, which cover very much the same ground as the example that we've just covered in this video.